Hello everyone and welcome to part 4 of the 3.5 notes where we're talking about rational functions. We're going to see now the third and the last kind of asymptote that we will deal with, which is this one that's called a slant asymptote. And the reason why it's a slant asymptote is because of, like it sounds, it is slanted. It is not one of these horizontal ones or one of these vertical ones. It will be slanted and it will resemble the graph of just a line like y equals mx plus b. Now, where a slant asymptote comes from, it comes from a situation where the degree of the polynomial on top is exactly one more than the degree of the polynomial on bottom. So like for this example, the degree is 3 on the top because it goes x cubed. On bottom, the highest power of x is the one that goes x squared. So the degree is 2. And since the degree is 1 more on top than it is on bottom, it's more by exactly 1. It has to be exactly 1 greater in top than it is in bottom. Then the graph of this function will exhibit a slant asymptote. And the way that we come up with it is bringing back this idea of doing the polynomial division. We need to figure out what happens when you do 3x cubed divided by x squared minus 9. And what's going to happen is that the quotient of this one, since the degree is different by 1, the quotient will be something linear. And then there's going to be a remainder that's going to be a rational function. And so why don't we just work this one out? Of course, we're not able to do synthetic division, unfortunately, because the bottom is quadratic. The denominator here is not linear, so we're not able to do synthetic division. But we are able to just rely back on the long division that we learned before. So we're dividing by x squared minus 9. And so x squared, we need something times x squared to become 3x cubed, so it would be 3x, of course. Then when we multiply these, 3x times x squared goes 3x cubed, and then it goes times minus 9, so it goes minus 27x. And then we're going to subtract these. And what we end up getting, of course, this cancels, just becomes 0. And then it goes, basically there's here some imaginary zeros and whatnot. But we would go into this one. We could do the x squared. It doesn't matter too much because, of course, we don't have an x squared term here either. There's like a 0x, and then there's a plus a 0 at the end. And so we're adding up these numbers, of course. That's why it's good to have a placeholder all the time, because we can stay more organized. I messed up my organization so they're not just vertically on top of each other, but we're adding, of course, the like terms, the x terms. And so we have 0, and then it's going minus negative 27x, so it goes plus 27x. And the degree now of the remainder is smaller than the degree of the divisor, so what we end up with is actually our answer, that whenever we divide these, 3x cubed over x squared minus 9, we get a quotient of 3x, and then we have a remainder of 27, so it would go rather 27x over the divisor from before, which was x squared minus 9. And so this linear piece, this quotient over here, this is the slant asymptote. And so if we graphed this thing, it would have an asymptote that instead of being horizontal or vertical, it actually is coming in a slant like this. This one also, if you think about what the vertical asymptotes would be, the bottom, we can factor this bottom, of course, like x plus 3, x minus 3. And then we can plot those. Those will become factors that will give us vertical asymptotes. So the vertical asymptotes would be the zeros for these factors on bottom. So basically x equals plus or minus 3. Those will be the two vertical asymptotes. So we could plot those vertical asymptotes. This one also, of course, there will be no horizontal asymptote because the degree is larger on top. But we would want to, and I'm going to have to extend these asymptotes a little bit for us to think about how to graph this one. If we were to graph it, of course, this is one that's supposed to be vertical. It ended up being quite slanted. But anyway, getting it as vertical as possible there. There's our slant asymptote. We would have to probably pick some sample points to figure out where this graph is going to go, where the graph of this one should be. Luckily, we're not really graphing this one, but what I would recommend is pick a number like maybe -4, and see what value you get for -4. Do you get something in this region up here, or do you get something in this little pocket, this kind of corner down here? That will determine whether the graph on this side looks like this, or whether maybe it looks like this on this side. It depends what the value is for f of -4. And then in here we could pick something like -1. That's easier to plug in. F of -1 is, of course, -1 cubed, 3 times -1 cubed over -1 squared minus 9. So -1 cubed just becomes -1, so it's like -3 on top. And then on bottom goes 1 minus 9, which is -8. So it becomes 3/8. And since the value is up here, 3/8 is some value up here, then we can be pretty confident that the shape of this one, thankfully we're not worried about graphing this one right now because this graph does not look that good. It is possible, by the way, let me make a note right here. It is possible for a graph, it can cross a horizontal asymptote, and it also can cross a slant asymptote. A function will never cross through a vertical asymptote. That's the point. And so here we can get all kinds of different shapes where we might be actually passing through this slant asymptote when we're in here in between these two vertical ones. And so that's always a possibility to think of. What I would recommend is just plugging this one into a graphing calculator, see what it looks like, and we will mostly focus on doing this kind of a graph, for example, graphing using the transformations like number 9, and we will graph ones that are a bit easier to graph, like that don't have such an ugly, basically, denominator of having these two vertical asymptotes, and by having a slant asymptote it just becomes very complicated. But anyways, it is always possible. It's possible to do, but we're just not going to do it in this video right now. And so here we want to use transformations. Do you notice what transformations are going on here? Of course, this -1 at the very end, this will shift down by 1. And when we're talking about these shifts, by the way, it's necessary to remember what should be the parent function, which I'm going to call g of x, the parent function for this one that we're looking at right now. And it can be a little bit difficult to identify the parent function for some rational ones. For example, this one that we did before, it's not really clear what should be the parent function for this type of a rational function from number 8. But for number 9, it's fair to say this rational function what it's talking about is the one that goes 1 over x. Because they're going to shift it down by 1 by going -1 on the end. And then they're subtracting 3 from the x right here. And so x minus 3, whenever you take away 3 from the x, this goes, of course, to the right by 3. And so the normal 1 over x would pass through -1, -1, and 1, 1. And it would have vertical asymptote on the y-axis, it would have horizontal asymptote on the x-axis, and then it would just be looking something like this. And so we're going to take this function and we're going to shift it down by 1. So in other words, the horizontal asymptote should come down by 1. The vertical asymptote should go to the right by 3. And then we're just going to fit the graph in there kind of the same way. It would just go roughly like this one. And we could try to be deliberate about, of course, this y-intercept over here, for example. We could be very exact with it. But this would do. This would be our graph of this one with the transformations. And so we're going to have one more quick video from this section where we will deal with an application for using rational functions, and then we will be done with 3.5 and we'll be getting ready for chapter 4. So thank you guys for watching this video, and I'll catch you in the next one.